Okay. I don't have any fun intros today, guys, but we're just going to pick up from where we left off on Monday. Let me get set up here. There we go. That up there. Put that there. Okay. Where's my little my doodad? My clicker. Don't have my clicker. Yeah. Here's where we're starting today. Data structures in there. Complexity. My chat there. That's good. Okay. Well, we'll get going here in a minute. How are the projects going? Clicker. Found the clicker. Okay. Okay. All right. We're gonna get started. Last class we talked about two things. We talked about the ideas of cohesion and coupling, which is basically if you have a nice, well-defined interface and you keep all the data encapsulated, you've done good cohesion and coupling. But it's more of a what to do versus what not to do. Today we're going to be doing a little bit more analytical, comparing different data structures that already exist. Okay, so on the left here, we have a bunch of different data types. Most of them you've seen. Okay, you've seen array, because it's just an array of items. It's templated with type T. We don't usually see it like that. We see it as an array of ints or an array of strings. But when you try to add something or find something or delete something from that, its asymptotically complex. Its asymptotic complexity is big O of n. Okay, trying to add with an array is O of n because it actually has to copy all of the elements over and then add one. So it's really n plus 1, and in big O notation we say that's just n. So adding to a, by the way, YouTube is telling me my audio stream's bitrate is 0. Can you guys hear me? So audio stream's current bitrate. So my stream is 0. Looks okay. Okay. All right. We'll just ignore YouTube then. Okay. So adding things to an array is relatively slow. It's linear time. Finding things, as we've seen, we've done searches in an array. You have to start at one end and work your way to the other end until you find it. Deleting, we haven't really done deleting, but it's the same as adding. You make a new array with one less element. Now, the only place where an array really excels is in the get by index, using the index or the square brackets. Using the square brackets, just move this over here. Using the square brackets, it's constant time, because the array is allocated in a chunk, and so it basically does a little bit of math with pointers and jumps directly to the place you need to get. Now, a linked list is a different type of data structure. We haven't seen that type of data structure. But the problem with a linked list is on the whole, adding things is actually constant time because it deals with pointers to other pointers. But finding, it's still linked. It's one points to the next, points to the next. So instead of being a contiguous block of memory, it's a bunch of chunks of memory. Each chunk has one piece of data in it of type T, and it points around to it. So adding is very fast because it's just adding one pointer. But finding, deleting, and getting by index are all linear time. So it's a little different from array. Array you can get by index very quickly, but by a linked list, you can't. You have to iterate over every element. It's very much sequential access. It's like trying to find the right song on an old tape deck. Not that you guys, anybody have a tape deck? All right, so there's this movie out called The Guardians of the Galaxy, and the guy from the 80s, he's got a Walkman, puts the headphones on, and it's a tape. He has to listen to it from start to finish. He can't just skip right to the song he wants. Okay. So then we've got list. List is what we've typically used. It's resizable, and it's really the best of both worlds because adding items is a constant time thing. Getting by index is a constant time thing. But finding things is still a linear. It's still a search. You got to search over every single thing. Stacks and queues are a little bit different. A stack from 263 or any programming course, a stack, it grows up from the bottom. So it's last in, first out, and a queue is first in, first out. Those have constant time because they basically have all the best parts of a linked list. And delete, same thing, because it's only dealing with that head pointer. Okay, so this table is extremely useful when you're trying to decide what kind of a data structure you should use. And there's a second part to this. So we've got array is linear time in most things except for get by index. List is constant add, constant get by index, but still linear find. Why doesn't this work when I want it to work? There we go. Okay. So here we've got some things where find is not linear. Right? Adding things to a hash table or a tree-based dictionary or a hash table-based set or a tree-based set. All of these are actually a little bit more detail-oriented. A hash table, as we talked about when we were doing the project, takes a key value to sort things by. I say sort loosely. And then the data is of type T. So adding, finding, and deleting things is constant time because of the way it's implemented. So the only downside is you're adding more memory. You've got a trade-off there. So then we have things like a tree-based dictionary, and that's interesting in that you can sort things based on different things. So we have a dictionary or a sorted dictionary, and because it's logarithmic, you can assume that this tree-based is some sort of binary tree. Each node in the tree has two tables. So say if you're dealing with the alphabet, maybe you've got a head node M, and everything on the left side of that M node is all closer to the beginning of the alphabet. Everything on the right side of M is greater than or closer to the end of the alphabet. But it grows with log time. So by doubling it, you only add one step. Okay. Then we've got sets. Sets are not the same kind of storage. With an array, you can have multiple elements that are all the same value, right? You can have an array where every element is the number 5. A set has an extra piece of logic in it that is really set in the set-based notation, math notation. So when you have this hash set, it's great for keeping things where you don't care if multiple instances show up. You only care if at least one has shown up. And then you have a sorted set. It's based, again, on a tree. So we've got a dictionary and a hash set, and then a sorted dictionary and a sorted set. But all of these are better in terms of the way that they can access the data by finding things, adding, finding, deleting. Okay. But they lack the ability to get by an index. because that's not what we're doing. We're not getting by an index. We're getting based on a key. Okay. So when do you use these? These are the rules of thumb we're going to use. If you want an array, that's when you have a fixed number of elements. And the fixed number of elements is because it's so painful to add. It's linear time. Now, it's not quadratic time, it's not cubic time, it's not exponential time, but it's not constant time. And you should always shoot for constant time if you can. So when you've got a fixed number of elements, you can use an array. When you need to be able to add or subtract, if you don't know how many things are going to be in, well, you use a list. Okay, so when do you use a list versus a linked list? Well, a linked list is, well, it says, if you want to add things to the end of a list, well, you can use the append method for lists. But for linked lists, you can put things at either end of that list. Okay, but if you can deal with just growing in one dimension as opposed to or one direction, if you need it to grow in two directions, you can use a linked list. Does everybody understand why the difference between list and linked list? List and linked list? Mirror, flip horizontal. Yes. List and linked list. Can't you also add things to the middle with a linked list? You can. So with this linked list, I haven't tried to do that. I would assume that if you look at the add method, it gives you an index as to where you can add. But this may be a subset of a true linked list. With a linked list, you can insert at any point. You're right. But with a list, you can't. A list is a very lockdown. You can append things to the end of the list, and that's the only place. If you wanted to append something in the middle of a list, it would be very time-consuming because you'd actually have to shift everything over. Okay, so stacks and queues are used when you need something to represent a stack or a queue. That's all I'm going to say on that. Hash tables, though, dictionaries, we've seen. When we want to add things quickly and be able to search for things quickly, a dictionary is definitely the way to go. Trying to remember, so there are periodically like Google interview questions published, and usually like 9 out of 10, the quick answer is to use a dictionary. You can actually find plenty of people. There was actually a former Facebook guy. He does like code interview, mock interviews, where he just presents problems and lets people solve them. And the answer is almost always a dictionary. So if you need to be able to search for things quickly, a dictionary excels at that. Because while it doesn't show it here, dictionary, oh, there it is, find. Find is constant time or near constant time, depending on how good the implementation is. So using a dictionary, when you need to be able to find something quickly by its key, not just by its index, okay? But the disadvantage is there's no order, okay? If you try to print them out, print out every element in the dictionary, you are not going to get like a traditional dictionary where you start with A and then go to B and C. There's no implied sort order there. It's just whatever the hash happens to be. Okay. But when you care about the order of things, that's when you can look for a sorted dictionary. Okay? So you still get all the advantages of a dictionary. You find things very quickly. But when you're enumerating things, they get sorted by key. And so this is much more of a traditional dictionary like you think of as a book. Okay. So then we get to sets. That's the last piece. A set is unique values. So if I create a set and I put in the letter A is in the set. If I put the letter B, then I'll have a set that has A and B. If I put in B, if I put in B again, I still only have A and B. I can put in B 1,000 times, but it's only ever going to be one copy. And so that's another useful thing. If you're trying to just keep track of, does something exist in a set? That's exactly what you've got. And then just like a sorted dictionary, a sorted set keeps track of in order. Okay. So this is actually, I think we left off at this last time. So both parts of this, the algorithmic complexity, is how many steps it takes. It can be logarithmic, linear, n log n, square, cubic, exponential. It should be clear, or there's also constant time, right? So constant time is the best you could do. Logarithmic is next. Linear comes after that. Then n log n, then square, cubic, exponential. Everything after cubic is just like not a good algorithm. But sometimes you have to. Sometimes there's no better option. Now, a lot of the reasons that things like these data structures can do things in constant time is typically because they use more memory. These are time benchmarks. They're the complexity in time. Okay. So we're estimating the speed. The fastest add, find, delete structure is the hash table for all these operations. Yeah. Okay. Questions about that? Because otherwise we're going to move on to the next lecture slides, I think. Or about the project while I get set up here. Okay, let's go into detail a little bit more then on hash tables. Okay. When do you think memory efficiency wins over time efficiency? Well, when you don't have memory, then you can afford to waste time. Otherwise, time efficiency almost always wins. It used to be when you were braiding your memory for the Apollo lander that your memory, well, actually that's really core ROM. That's not a fair consumption. It's not a fair comparison. But if you're doing something with a microcontroller, where are all my microcontrollers here? I usually keep 2 or 3 around. So here I've got a Wi-Fi module. It's a 32-bit microcontroller. I don't think I've done anything with it, but it's an embedded system. Even this embedded system has a couple megabytes of RAM, I think. That's millions of bytes of RAM. The 328P has 2K of RAM. So if you cannot support the data structure in memory, you're not going to be able to use it. It's just the way it works. So when does memory efficiency win over? When you've got the memory to spare. This is one of the big differences. My opinion, this is like the comments are going to come in down below about what a horrible human being I am. This is the big difference between computer engineering and computer science. In computer science, you have more resources than in computer engineering. The whole point of computer engineering is to be able to do things with as little as possible. Okay. Dealing with very small amounts of resources. In computer science, sure, you can design algorithms that work with very small memories or very small resources, but more often than not, you're targeting something that has lots of resources. It's scalable. If it doesn't have enough resources, throw more resources at it. Okay. So that's that. Any other comments, questions? All right. So we're going to go into, in case you missed it when we did the review, we're going to go over dictionaries and specifically using the dictionary class, okay? And then a little bit at the end with sets. Okay. So the images are actually pretty helpful because with a dictionary and a thesaurus, they both have the same basic structure, right? You look up a word and it gives you some information about the word. In a dictionary, it gives you the definition. In the thesaurus, it gives you a list of similar words, words with similar meanings, right? But in both cases, you're looking up based on a keyword. So the dictionary is an abstract data type. It's not something that's one piece of data. It's not an int or a float. It's a lot of things together. You'll hear it, depending on where you go, you'll hear it called a map or an associative array. Big research right now is happening in associative memory, which is like a dictionary inside of RAM. It contains a bunch of pairs of data, though. A key, and that's what we're looking up based on, and then the value for that key. So, for example, I gotta think of a word that has good and clean and wholesome synonyms. Cold. The word cold has many synonyms. Go ahead, list them in the chat. Think of synonyms for cold. Okay, cold is our key, but all of the synonyms are our values. Okay, and so with a dictionary, we have some basic words that we can, your basic methods we can use. We can add things. We can find things based on the key. So if I say add cold, comma, frozen, brick. Is brick a synonym for cold? Brick. I'm not so sure. Is that like a slang? I'm thinking of just a 4 by 3 by 6 block. I don't know. But the point is, everything we're doing is we're operating based on the key. So even though you're giving me a bunch of synonyms, those are values, or really the value would be an array of those words. And we can implement these dictionaries, these maps, in many different ways. And we talked about them just now. You could do a sorted dictionary. Yes, it's very slang. Okay, I learned something new. Let's not get personal, guys. Let's slow down. Let's be nice to each other. We're all in this together, socially distanced. Look, you hurt his feelings. Stop that. Okay. Dictionary, okay. So how does a hash table work? A hash table is not what it sounds like. It's actually taking a function of whatever the key is. So if the key is a string or an integer or some other data type, there is a function that reduces it down to some number, okay? And that number is used to index into an array. So if we take the word cold, maybe it has a hash of 7, okay? So when we hash cold, every time we hash cold, it's going to give us the number 7. And a good hashing function will make it such that no other word will hash to 7. It's harder in practice than it sounds. But if we had a perfect hashing function, every word or every key would map to a different hash number. And that's what this is saying here. The hash function of k, your key, maps to something between 0 and m-1, where m-1 is the size of your array, the size of your storage. Okay. So everybody with me so far on what hashing is? Okay, because that's the basis of everything that goes beyond this. Okay. So in a perfect world, it would be very easy to take every word and reduce it to a number, especially if you had infinite numbers, and numbers are infinite. But a computer is finite. So we have to reduce our hash table from infinite slots to some limit, so 0 to m, where m is probably a power of 2, right? It's probably 1024 or 4 billion, okay? But the point is that whatever our hashing function is, it knows that it's going to map within that. And the quickest way to keep things bounded, especially if we're dealing with power 2, is modulus, right? We can modulus whatever the number is. So it gives us an infinite number, and we only have, let's say, 32 slots. If we mod by 32, we'll always end up with a number from 0 to 31. Now, what that does mean, though, is sometimes two things that are 32 apart from each other will end up with the same hash number. Okay? So the perfect hashing function doesn't have that problem. It will always map correctly. But it's usually not that probable. Realistically, we map it into a subset, but it won't be unique for every input. For most common inputs, we'll have a unique output of the hashing function. So when we do have something where two different keys result in the same hash, we call that a collision. And if we can keep collisions down, it's not actually really a problem, because there are ways to resolve collisions. Let's talk about this for a second. Let me get my pen. Let's open up Open Board. Okay. And let's go here. Where's my... Okay. And then I've got to go like this and say Open. Okay. So here is how we might represent a key value pair. All right. First thing to know is that we're dealing with some contiguous memory here. All right. And to make things simple, 1, 2, 3, 4, 5, 6, 7, 8. I'm going to have 8 items in my hash map. 4, 3, 2, 1. Okay. And what we're going to do is we're going to create a very trivial dictionary. And the goal is to take bytes and map them into this hash map here. So a byte could be any number from 0 to 255. And I've got 8 items. So here's my hashing function. I'm going to take, hash of key is equal to key ANDed with OX07. This, by the way, is a bad hashing function. But it will get the point across. So every time I do this, I'm going to create an object. Where's my pen? Okay, so the first object I create is going to be the number 55. And what I need to do is hash that function. And I'm going to just cheat here because I don't want to make a mistake. Be awkward. So 55 is going to be 7. Okay, if you AND 55 with 7, you end up with 7. So what that's going to do is it's going to take, and 7, location 7, is going to point to the 55. Now let's take another number. I'll take a volunteer number if you like in the chat. What number? Remember, it's got to be a byte between 0 and 255. 77. So 77 maps to 5. Maps to 5. Okay, 69 maps to... Ooh, here's a problem. 69 also maps... 69 also maps to 5. So we have a choice now. This is our first collision. Up till now, these don't point to anything. Okay. Up until now, it was easy. You just take wherever the array pointed and point it to that particular block. But now we have a problem. 5 is already taken up. So the simplest method of what's called collision, so if you take the hash of 77, that is equal to the hash of 69, which is a problem. We have a collision. So in the worst case, or rather, not the worst case. Just the simplest way to solve this is to actually take and say, all right, well, 77 will point to 69. So if we want to redo this, we say we want to find 69 again. We take the hash of 69, which is 5. Excuse me, 5. Take the hash of 5. So we go to location 5. And we say, okay, 5 points here. Is 77 the thing we were looking at? No, it is not. So we go one further. We follow it again. Is 69 the thing we were looking for? Oh, it is. So we're done. So how does that change when we have, so let's take some other number. Let's say 61. If we hash the number 61, let's make sure I'm not lying here. 61 also hashes to 5. So if we hash 61, it's 5. So we go to location 5. We'll go in blue here. We go here, and we say, okay, that's 77. Is 77 correct? 77, 61? No, it's not. We follow it again to 69. Is 69 the thing we're looking for? No. Is there anything else? No, 69 doesn't point to anything else. So as a result, we can say that 61 is not found. Okay, that's one conflict resolution scheme. Go back here. Okay, so that's what we call chaining in a list. Another option is to use neighboring slots. And this is a different way of doing it. So instead of putting 69 as a chain, go back to open board, right? Instead of doing this as a chain, we would still have our list of items here. 1/2, 4, 8. So what were the numbers we put in? We put in 77 first, and that fit into 5. 0, 1, 2, 3, 4, 5. So we put 77 into this. And then the next number we put in was 55. That went into item 7. And then we put in 69. And 69 should have gone here. So instead, we could put it in one of the adjacent cells. You can obviously see that this is only going to work a few times before we start having no space at all. Okay, so and then to find things, we'd actually have to go in here and then say, okay, it's not 77, and then start hopping in a direction. So basically, you've turned it back into a linear search. Okay. So that's why it's a linear program. The other option is you could rehash using a second hash function, or there's lots of different ways to solve collisions. Go back to my lecture slides. All right. So, and here's another example, same type of thing, where each time we do it, here we're hashing strings. They still result in an integer. And we've got these pointers. We point to different items. And since Kiro and Ivan hash to the same number, number 2, they just go in there. Okay. So the only complexity is the hash function. And since the hash function should run in the same, in the same amount of time for any data type, okay, we can do it very quickly. So it's a constant time operation. So adding, finding, deleting, they all take very few operations. And it doesn't matter the size of this array. If M is 1,000 or 1,000,000, it doesn't really matter because we're just doing pointer arithmetic. That was the big takeaway of a standard array. A fixed size array is instant or constant time access via index. So all we're doing is we're hiding the index behind this hash of the key. Okay? So here is the actual .NET implementation. Okay, the .NET implementation has a dictionary and a sorted dictionary. They're based on an interface. Okay, both of these things have the same stuff. They're based on this interface called iDictionary, interface for dictionary, which is itself inheriting from the interfaces of collection, enumerable, and enumerable. One has key value pair. So key value pair is a type in .NET, and it's just two types. So we could have an iCollection, and maybe we should look at what these do. Okay, so let me actually just stand by here for a second. I want to have Visual Studio open because I want to show you what's going on here. Put you here. And class diagram. I know you can't see this, but I will. I'll get it there in a second. Okay. Container. Nope. Adventure. Program. Yes. Class diagram. Hello. Program. There it is. Go to definition. Okay. Go over to Visual Studio here. So here's our starter project that we did last week. Here is the dictionary class. It's in Systems Collections Generic. And it implements quite a few things. It implements the interface collection, the interface enumerable over a bunch of key value pairs, enumerable in general. It also implements iDictionary, which is the important one. And then a few other things, read-only collection and read-only dictionary, iCollection, iDictionary, deserialization, and serializable. Okay. So what does iDictionary actually do? Let's go here. Go to the definition of iDictionary. All it does is say that you're going to be able to index based on a key. You're going to have a collection of keys and a collection of values. You're going to be able to add and remove. And you're going to be able to try and get a value out, as well as see if a key exists. That's it. So this just tries and assumes that the key exists. It's also how you can actually set items as well. Contains key just checks to see if the key exists but doesn't access the value. And then try get value tries to do a read on that key but doesn't crash. It returns a true or false based on whether or not it's able to find the key. This, if you try to read from a key that doesn't exist, it throws an exception. It returns 3 different exceptions. Key not found is the one that you'd see most often. If the key is null, it'll throw an argument null exception. Okay. And so this was done just by going over to a, program, right-clicking on the My Rooms dictionary object and saying, go to definition. That was the dictionary. So going to iDictionary here, going to the definition of that, that's where I see adds, contains, removes, and the keys and the values. That's all it's doing. Now, these are read-only. Internally, there's some private way that it's holding on to the data, but that's not what we're looking at here. Go back, because I also want to talk about iEnumerable. Or not iEnumerable, yeah, I want to do iCollection first. iCollection is what you typically would think about. Okay, an iCollection, you can add items, clear the whole dictionary, see if something exists inside the dictionary. Okay, but it's based on a key value pair. So T is actually a key value pair. So you could construct a key value pair, some number and some string or something, and see if it exists in the dictionary. Okay, so this isn't finding based on key. This is finding based on the whole unit of the key value pair. All right. The last thing I want to show you, second to last thing, is IEnumerable. Enumerable just has this one method called getEnumerator, which you probably have never used before, or so you think. Having something that returns an enumerator is what actually happens when you're using a for each statement. So saying that something is enumerable means you can say for each item in blah, blah, blah. Now, the difference is here, T is a key value pair. So when you iterate over a dictionary, you actually iterate over a key and a value stuck together. Okay? Okay, so there's one last thing that you can do with a dictionary. It's all the way at the end here. Called iSerializable. Okay? And serializable is one of those things that we haven't talked about yet, but it's worth mentioning now, especially if you're going to try and implement some sort of a save feature in your game. Because the idea of serialization is you take an abstract data type, something very complex, and you reduce it down to some sequence of bytes, whether that's text or binary. You reduce it to something that can be reversed. So if you're reducing it down to text, it might just be XML or JSON or some sort of SOAP or something, but it reduces it to text in such a way that you can read the text back and return the exact same object. So if you created a game class that was serializable, you could save the whole game to a text file, and when you opened that file up again, you would be able to be exactly where you were when you started. But things that you have to keep track of are things like your current position, the position of all the dwarves, the position of every item, the contents of every room. But, and here's the kicker, if you create a serializable room and a serializable item, you can just say, okay, serialize and go back to what we did, right? We have a dictionary of rooms. Serialize the dictionary of my rooms, which will serialize the dictionary. But then the dictionary will call the serialize method for adventure room. And it will then be a quick way of saving everything. Okay. Heading back into Foxy here. Come over here. Do that right? Yep. Okay. So for a dictionary, the size is dynamically increased as needed, which is very nice, which means you don't have to worry about collisions quite so much. If you do find a collision, it creates a larger thing, so you don't have to worry about that. But it does have chaining. So in the worst case, imagine you had an M, a hash size of 1. Everything would hash to that one location, and so you would have everything would be a collision. And at that point, you have a linked list. So that's not a good implementation of a dictionary, but it's something that could happen. So in the very worst case, actually, this could be something like linear time. But because of the dynamically increasing size, typically that doesn't happen. Okay. So the only thing you need to make sure, if you're trying to do a dictionary of something, say a dictionary of adventure rooms, it is important that adventure room implements, or sorry, I take that back. This is for the key, okay? The key has to have these two properties, not the value, but the key. So the key has to have an equals method to make sure that two keys are not equal, because all it's doing is checking to see if it needs to chain things. So you have to override the method object.equals. That really is object.equals, because object is the base class of everything. So equals just returns true or false, I think, for whether or not something is equal. And then there's a method called getHashCode for calculating the hash code of the key. So if you're doing integers or strings or any built-in .NET type, those are already included, right? But if you're doing some kind of a key that you have created, maybe a complex number class, you have to implement getHashCode. The advantage of the .NET framework is they actually make it pretty simple. You can take two hashes and combine them. There's a method to combine hashes. So if you're based on two underlying types, say in the case of the complex, two floating point numbers or two integers, you can take the hash of both of those numbers and then do a hash combine, and you'll be able to get your hash. So it's not that complicated as it used to be. You had to do the research and decide what kind of a hash function you're going to use and these sorts of things. Don't worry about it. But it is up to you, though, to write that get hash code function. Okay, so a dictionary, we can add things, we can remove things. And as we saw, those are from the collection interface. It's not based on the dictionary. It's just every collection. The indexer, though, that is part of the iDictionary. Okay, we're doing it based on a key. Also, see how many things are in the dictionary. When you say keys and values, that's actually a collection of the keys. So it basically strips the keys away from their values. You just get the keys. And then you can also get just the values, okay, stripped of their keys. For us, we've got two, and one of these is very good, one of these is not so good. Doing a contains key runs in constant time, because all we're going to do, well, worst case I think might be linear, but constant time. Because all we're going to do is hash the key argument we provide and see if there's something there. If there is, it's just a true false. We're just looking to see. Even with collision chaining, it's either it's there or it's not. But contains value is not a good operation. You can do it, okay, but you should be aware that it's going to do a linear search through all the values. Okay, keys can be hashed and quickly get to the location, but contains value, you just got to look at every element and see if the value for that element exists, and that's all you can do. Try get value does run in constant time. It has the added benefit of not throwing exceptions, but there's some extra logic you have to do. You have to pass in the out variable. You have to check the result to see if it exists, see if it returns true or false. Okay, so here's an example, and I think we'll end. You know what? Let's start next class with this dictionary demo. Okay. Oh, I haven't had my chat up for a little bit. So we can add features like that to the game. Yes. I would encourage all of you to try to do one added feature. Just pick one, do what you like, because adding that constraint to yourself is going to make you a little more creative. You, at the very minimum, have to be able to walk around, pick up items, get a score, okay, and interact with the dungeon or the cave, okay? If you want to add a new feature, like a debug mode or a cheat mode, first off, the cheat mode might be considered a debug mode because basically you could jump to any room that you want. So if you see jump and then a room number, you know, if there's certain things done, you've somehow enabled cheat mode by typing certain commands, that's fine. And it's a great way of, during your demo, remember, live demo, showing off what you've done, saying, oh, look at this. This room, we've implemented the oyster being correctly manipulated, or we've successfully implemented the word plu and it suddenly works, or plover, okay? Just so we're clear, I don't expect that everybody's going to get the game finished. You're graded based on what you chose to implement and how you implemented it. You do have to have certain minimum standards. You got to be able to load up all the pieces of the file. You got to be able to print out the rooms. You've got to be able to handle movement and basic commands. Certainly the ones that we talked about in class that we did, okay? Everything after that gets a little more complicated, okay? So you guys should be keeping track of what words you have successfully implemented in what situations. We talked about looking at, I've got to get out of this and go over here. Oh, what did I do? We talked about looking at the special words, the vocabulary words. Ooh, too far. So anything in the 2000s was a word that was going to require you to do some things in order to make them work. And certain words work differently in different rooms. So if you're going to implement the word wave, I think we can actually find. So wave only works in one room. Okay, it works if you're waving the rod at the fissure. Okay, which we actually showcase. If you wave the rod, a crystal bridge appears. Okay, and we change the state. But there's a bit of testing we have to do. We have to check if we are holding the rod. If we're holding the rod, we have to. If we're not holding the rod, we say something snarky. If we are, we have to check whether the cave is closing, which is sort of end game stuff. We update the property of the fissure to say that, hey, there's a crystal bridge here. And then we speak the fissure line. Okay. But for things like attack has a lot of things going on. Okay. Attack has many, many options. This is a much harder thing to implement. Okay. Pour is another one of those very complicated words. So you have to choose what's going on. Things like eat might be pretty simple. Okay. Drink might be pretty simple. Apparently saying rub yields nothing but snarky remarks. Okay. So some of these words are easier to implement than others. Okay. So that's just a quick way that you can start looking at these words. There's a whole group of words in the 3000s. Those are very special words that do some interesting things. Some of them are easier to implement than others. Okay. So as you start working in earnest on this project, we only have a few weeks left, and then we've got presentations. Start thinking about what words you're going to implement, what locations you're going to implement them for. So maybe you don't implement them for everything. Maybe attack doesn't work on the dwarves. Maybe it only works on the snake or the dragon, or one or both, or includes the bear and the troll. It's up to you. Okay. Obviously, the more you do, the better you do. But we're looking for interesting creative approaches here. Okay? Any questions? Okay. Well, that's it, guys. I will see you on Friday. If there is something that you want me to cover that's really got your head scratching, leave a comment in the video or send me an email. And we'll try to cover it if we can in class. If I think it's giving away the store or the farm, what do you give away? Giving away secrets, I'll say I can't do it, but the worst I can do is say no. All right. I will see you guys on Friday. Hope you're all staying safe and not going stir crazy. And I will see you at the end of the week.